Hi, this is our Chapter 12 lecture on mass spectrometry and infrared spectroscopy. These are two of the four experimental techniques that we learn about in this year-long course here. We learned about NMR, nuclear magnetic resonance spectroscopy, last semester. If you need to review up a little bit on NMR, the videos are still linked from our current webpage. I have a link to last semester's videos, so go back there and review up on NMR if you need to. We'll be making use of NMR again in lab quite a bit this semester. Not quite as much in lecture, but we'll make a lot of use of it in lab. So NMR is very useful because it gives us the carbon-hydrogen framework, tells us what kind of hydrogens are present, how many neighbors they have, lots of excellent structural information about organic molecules in NMR. This chapter will be dealing with mass spectrometry and infrared. MS gives us the size and the formula of molecules, as well as some structural information, what kind of fragments could break off a molecule, for instance. Infrared tells us about functional groups and what types of bonds are present, essentially. The next chapter we'll be studying, we'll talk about ultraviolet, where we learn about conjugated systems. So let's start out with mass spectrometry. Like we said before, it measures mass and molecular weight, essentially, of molecules, so we can get additional structural information from fragmentation, and we'll talk about that quite a bit in just a little bit. But essentially, if we want to know what the molecular weight is of a molecule, we can ultimately figure out what its molecular formula is, oftentimes, and get a good amount of structural information. So just the flow diagram here for what happens in MS, we have a sample. That sample is ionized. So whenever something is ionized, it goes from neutral to having some type of charge to it. So we're going to talk about electron impact pretty much exclusively in here, but there's also electrospray, there's MALDI, matrix-assisted laser desorption, ionization. All of these serve to impart some sort of electronic charge on the sample that's necessary for the next step. The electron impact ionization that's most common for small molecules. What happens, the sample is vaporized first. Oftentimes, the sample runs through a gas chromatograph, much like the one that we've used in lab before. This can separate out impurities and so on, but that's not always necessary. If you're confident there's a pure sample, it can be directly injected into the mass spectrometer. The vapor phase sample is bombarded by a stream of electrons, which actually removes one valence electron from the molecule. It's a little counterintuitive, I know, but if you hit it with a stream of electrons, it'll actually knock one electron free. So what we have here is an organic molecule to start with. Here is our stream of electrons, and what we end up with is what's called a radical cation, or cation radical, plus some electron that's been given away. It is a radical now because it's an odd number of electrons. It's a cation because we've lost a single electron. So mass spectrometry is one of the only places where we run into this radical cation type structure that has the plus and the dot symbols next to it like that. So the radical cation is the species that, for the most part, is directly analyzed in mass spectrometry. So that's what electron impact is, just like it sounds like. Stream of electrons knocks one electron away, gives us a radical cation. These other ones are kind of interesting. Like I said, this only really works for small molecules. If we have large molecules, like big proteins or something like that, it's tough to get them just as a stream of vapor in the first place. So electrospray, what happens is a solution with the sample that you're analyzing is sprayed, and these tiny little droplets form, and through the process of the solvent evaporating from those droplets, a charge can form in there. MALDI is pretty neat because what you end up having is a sample that is placed on some sort of matrix, so some sort of substance, and a laser strikes it and pretty much explodes the matrix, and the sample ends up getting ionized and airborne in that process too. So we won't talk any more about those. Let's just deal with the electron impact. Once it has been ionized, it goes to a mass analyzer. We'll talk about that on the next page, but it just essentially sorts these ions by mass so that they can be detected by the detector and eventually sent to a computer to be displayed. So ionization just gives us a positive charge so that it can go through the mass analyzer and eventually the detector. The spectrometer itself, this is a bit of a schematic diagram, just like we talked about. A gaseous sample comes in here. There's a electron beam that comes from a filament that is bombarding electrons in that sample. The sample is directed into this curved tube, in this case, by a series of electromagnets or a carrier or something like that. Two powerful electromagnets are placed at the bend of this curve, and that will alter the trajectory of these charged molecules. So the ions are deflected according to their mass and their charge and leads to the detector. This is what an actual machine looks like. Actually, most of this is gas chromatograph, just like I mentioned, where the sample is just vaporized and separated based on its boiling point, for instance. And then over here, this little box, it's just attached directly to the outlet of the GC, where the vaporized purified samples can go into the mass spectrometer, something like that. Something that's interesting to us that we'll get to in a little bit is that most organic molecules will fragment when they're struck by that electron beam. So not only will they be imparted with some sort of charge, but the carbon bonds, for instance, will actually break, and the molecule will split into smaller fragments. The ions, whether it's the whole molecule or those fragments, they're all sent through this curved channel. They're deflected based on their mass to charge ratio. That's the mass and charge are both two things that affect the way that the particles are deflected by a magnetic field. So large molecules end up being deflected less, right? And that's just because of inertia. A large molecule needs a larger force applied to it in order to change its path. Smaller ions will be deflected more, so just simply size is the most important factor, but mass to charge ratio is important because a larger charged molecule will also be deflected more. So with the electron impact ionization, though, charge is usually just one, right? Usually a single plus charge in a small molecule is very common. So we can essentially assume that if the charge is 1, we're just dividing by 1. So this mass to charge ratio is just essentially the mass, right? The molecular weight, if you will, of those molecules. So the apparatus here that has this curve with the magnet in it, that just separates the molecules by their mass and allows them to make it to the detector. The detector just records the ions that make it through that curve. As that magnetic field changes, the particles are sorted by mass and a mass spectrum is produced. So we're going to have this m over z, this mass to charge ratio, which is essentially just the mass of these ions. That'll all be on the x-axis, and the abundance of those ions, how many of each of those masses made it to the detector, will be on the y-axis.